All right.
All right, so this is our EEE 174 heliostat project, and I'm Joseph Munoz.
So Garcia. Yeah, so a little introduction and objective. So what is a heliostat? It's just pretty much a device that will track the sunlight using solar panels or sometimes using mirrors as well. So our goal was to build this using the STM32 board. And it's important just because it increases the power produced from the sun more effectively.
So the smart architecture, the key components we used were an STM32 board. We used two different solar sensors or solar panels, which we used to measure the voltage from each of the panels. So in this instant, we measured across one axis, so just the horizontal axis. So essentially what it does is the panels will measure a voltage and the difference between those voltages. It'll remain in an idle state when there's a certain difference or a threshold, and it'll turn left when there's a higher potential voltage on the left, or turn to the right when there's a higher voltage on the right. We use an OLED display to display the voltages on the left panel and the right panel, and an SG90 servo motor to achieve rotation.
So following some of the not optional, the labs that we got to choose from, lab 5 and 6 specifically, I was able to actually follow a little bit of the analog to digital converter lab, as well as the OLED I2C display lab, and just change a little bit of the code just to make it work for our solar panels. And here on the right, or on the left side, is the code that pretty much sets our cursor and writes which voltage is where. This is a really small picture, but pretty much on the top we have the voltage on the left, and then the bottom is voltage on the right, and then up here is what's actually in the loop. So it's reading the voltage and doing the calculations up top, and here's what's writing these calculations, or the actual value of the voltage on the LED screen. And again, it's really small, but it's there.
So the control, logic and motor control, this is the code that I use. So we have a tolerance. It's a constant set above. I think I set it to like 0.1 volts. And then we have a servo position. This is kind of the trickiest part for me, was getting the pulse width modulation to work, because the servo motors take a PWM signal. In our case, it was 250 to 1250. So that gave me a little bit of a challenge. I started on the L432 KC board, and then I had to move to the F103 RV board, because the L432 KC board only had one ADC input. So whereas the F103 RV had two ADC inputs. But I was able to do the calculations to get a 50 hertz signal to the servo motor, which controls its position. So that's the code that I have controlling the motion of the solar panel array.
And here in the end, we have a video of the results.
You can also see here that when there's a higher voltage detected on the left, which you can see on the screen here, it comes to like an equilibrium point, but it follows along with the strongest light source.